Howdy class. So now we're going to be starting chapter 4. So the first part of chapter 4 is uh, learning about the periodic table. So we already talked about the periodic table a little bit, but now we're going to explore it from a new point of view, I'd say. So 4.1 is a really short little chapter, a lot on the history of Mendeleev's periodic table and how we developed the modern periodic table. So as a refresher, Mendeleev's periodic table was revolutionary because it accurately predicted the properties of several elements before they were even discovered. So in Mendeleev's periodic table, mostly he wanted to arrange the elements in order of increasing atomic mass. But every once in a while, he would find things that didn't quite work. For example, when he got to tellurium, that's in your textbook, they discuss this a little more. Tellurium had a atomic mass that was higher than what he expected based on its properties. Same thing went for argon and potassium. Argon actually has a higher atomic mass than potassium does, but if we switch them on the periodic table to make them in order of increasing atomic mass, they don't fit in with their families anymore. So potassium has lots of properties in common with the other alkali metals. So that's the first group on the periodic table, group 1. And then argon over there in group 18 has a lot of things in common with the other noble gases in group 18. So he decided to group them based on properties, even though the original idea was to group them, or order them, I should say, order them based on their atomic mass. And they didn't know why at that time. So it took a little while for scientists to discover new things about the atom, which we now know. We learned in chapter 2, when we first talked about the periodic table, that the periodic table is organized by the number of protons, which is called the atomic number. So a guy named Moseley discovered this property before he even knew what the atomic number corresponded to, before they knew the structure of the atom and they knew about protons in the first place. He found out that when you use X-rays, you shoot X-rays at these different types of atoms and different frequencies are observed. So those frequencies corresponded to atomic number, not atomic mass. So most of the time it corresponded to both, but every once in a while, like argon and potassium, we found these exceptions where it corresponded to this undiscovered atomic number instead of the mass. So we'll take a look at this again. So just to prove my point, argon over here in group 18, it has a mass of 39.948, and potassium has a mass of 39.0983. So they are only grouped together because, or they're only put in order of the way that we see them because of their properties. So over here we've got alkali metals. Potassium is a metal. It fit in with all of those. It had very similar properties. And then over here on the other side, argon was actually the first discovered noble gas, but they knew argon is a gas. It's not like the alkali metals, which are all solids. So they didn't, Mendeleev really didn't want to put argon over there, even though the traditional way of ordering the elements based on their masses would have told him to do just that. Okay, so that's about it in chapter 4.1. So let's talk about 4.2, where we get some exciting new terms to go along with our quantum numbers that we learned, and it will actually also go along with the organization of the periodic table, as we'll see in a bit. All right, so this is something that really probably should have been included at the end of chapter 3 with the atomic orbitals, but it wasn't. So we're going to talk about the energy of atomic orbitals in multi-electron systems, or many electron systems, now, since we didn't talk about it then. So a single electron atom or system is hydrogen. That's basically it. All of our other elements have more than one electron if they are neutral atoms. And we'll start talking about ions later in this chapter as well. But for now, so single electron atoms, this we did see in the last chapter. The energy of the orbitals just depended on the value of n. So 2s and 2p had equal energies. 3s, 3p, and 3d had equal energies for hydrogen. That's not the case for multi-electron atoms. Multi-electron atoms, we see something called splitting in these energy levels. So for example, the energy level, the n equals 2 energy level split into the 2s and 2p orbitals, and they have different energy. Same thing happened with 3p, 3s, 3p, 3d, and 4, n equals 4, n equals 5, n equals 6, so on. So we still have this general rule that when n increases, the energy increases for orbitals with the same L. So, for example, the L's are grouped together vertically, whereas the N's are grouped together horizontally in this figure. So if we just look at our N's for the same L, so all of our S orbitals for any shell, as we increase N, we increase the energy. If we look just at the p orbitals, as we increase N, we increase the energy. If we look just at the d orbitals or f orbitals, same thing. But then, as L increases, we also see that. So this is where we get these diagonal increases. So now these diagonal lines or groupings have the same value of N, but different values of L. So as L increases, so does energy. It's going up in kind of a diagonal fashion, according to this graphic. So as N increases, subshell energies become more closely spaced and overlapping occurs. What does that mean? So that means that the higher the value of N, let me erase so that you can see this a little bit better. So as we go up, there's a lot more overlap here. These three energy levels are pretty close together. These 3 or 4 energy levels are pretty close together. So as we go up, there's less separation. So 2s and 2p were pretty well separated. These are pretty well separated, but as n increases, our subshell energies become closely spaced and we see some overlapping. So to determine which ones are higher in energy, there's this method called the n plus L method that they will suggest for your homework, where we add those together. So for example, let's look at the 4s and 3d scenario, where 4s is our first anomaly in the filling or the energy levels based on our n and L values. So 4s, so n equals 4. The s orbital means L equals 0. So our sum is 4. For 3d, n equals 3. The d orbital means L equals 2. So our sum is 5. So because our sum is bigger, our energy is actually higher, even though it doesn't fit with our first main rule about increasing N, and it doesn't agree with what we saw for the single electron atom. Okay, so that's your shortcut way of doing it. It doesn't always work. For example, 4p and 3d, they're going to have the same N plus L. So then you have to go back to the first rule. Okay, awesome. So this is just another explanation for these multi-electron atoms. If we look back at our atomic line spectra, which we had a lot of fun learning about for hydrogen, we can compare hydrogen and helium. So hydrogen only had these 4 lines in the visible range, and that's because hydrogen doesn't have as many transitions allowed because their energy levels are the same for 2s and 2p, and 3s and 3p, and 3d. But for helium, those energy levels start to split. So we've got this, or this, or this. We can go from 2p to 2s. We've got 3s to 2s, 3p to 2p, or 3p to 2s, or 3p all the way down to 1s. We've got lots more options, so we end up with more lines in our spectrum because these arrows that I drew, these energy transitions, once again correspond to the photon that is emitted when that transition occurs. So that's why we see more lines in our spectrum. We have more types of photons that can be emitted. All right, so let's have a little practice here. Which orbital has the highest energy in a hydrogen atom? Well, hydrogen, it just depends on N. So hydrogen is our single electron system. And it only comes down to the N. So our correct answer for the hydrogen atom is C. But what about in a multi-electron atom or many electron system? So for a many electron system, we need to look at N plus L is our shortcut. So what do we see here? So let's just do them all. So when N is 5 and L corresponds to F, so F is 3, we get 8. So we get 8 for 5F. What about 3D? So we've got 3 for N, and D corresponds to L equals 2. So we've got 5 for that one. So that one's out. That one's not the highest energy. What about 6P? So 6, we've got N equals 6, and the P corresponds to when L equals 1. So that one's 7. And then 4S is going to be N equals 4 plus the S orbital is L equals 0. Sorry, that's a 0. So that one's 4. So 4S is the lowest energy in our multi-electron atom, even though 3D is lower energy in the hydrogen atom. But 5F and 6P, it gets a little weird. It gets a little hard to decide. So we do our N plus L shortcut, and we find out that 5F is actually higher energy than 6P in the multi-electron atom. So we see a distinct difference here in these two types of systems. And we can check if it's on one of these. We can go back here and check and see that our 5F is up here and our 6P is a little bit lower. If this is in increasing energy, energy is increasing as we go up these energy levels. So we got it right. Cool. All right, I'm going to stop here and then start a new video for the rest of chapter 4.2.